Hello everybody and welcome to this video about atomic structure for A-level chemistry. And in this video we're going to be looking at fundamental particles, mass number and isotopes, electronic configuration, so that's the arrangement of electrons around the nucleus, and this concept of ionization. So we'll be looking at what ionization is and how we can work out patterns for ionization energy across different periods and down different groups. Now this video is an excerpt from a larger video that is the whole topic review. What I've done for this video is I've taken out the section about the mass spectrometer and about how you work out the relative atomic mass of isotopes. First up, we need to take a look at fundamental particles. At GCSE level, you will have learnt about the different models for atomic structure, and over time our understanding of atoms has changed and developed as new evidence was discovered. First of all, we had the billiard ball model, which is the idea that atoms are all like a snooker ball and they're just one solid lump. And then that changed over time with the discovery of the electron to become the plum pudding model, where the idea was that an atom was still a solid lump but had electrons wedged around through the atom, and the metaphor is like it's the plum pudding is like a cake and the electrons are the rest of the atom, which is little tiny raisins or pieces of fruit. And then that model changed with Ernest Rutherford's experiment with gold leaf, and we got the nuclear model, the idea that atoms have got a very small central nucleus and electrons are around the outside and most of it's empty space. And then that model changed over time to the Bohr model of the atom, and that consisted of the electrons arranged in energy levels. So the nucleus of the atom contains the protons and neutrons, and these are held together by what's called the strong nuclear force, which is as the name suggests, the strong nuclear force is a very, very strong force, far stronger than the electrostatic attraction, which is what we get that holds these electrons in place around the atom. This is the electrostatics. And the nuclear force is much stronger than the electrostatic force that holds these electrons into place around the atom. And so these protons and neutrons are held together by the nuclear force, and they are referred to as nucleons. So the things in the nucleus are referred to as nucleons. When we look at protons and neutrons and electrons, they are absolutely tiny. And so when we're thinking about how big they are, we don't look at their actual mass, because the actual mass of a proton is something like 1.67 times 10 to the minus 27 kilograms, and their charge is even smaller in terms of the coulombs of charge. So we compare them and we say a proton and a neutron have got the same relative mass, and we give that a mass of 1. And when we compare it to electrons, electrons are almost 0 but not quite. It is 1 over 1,840, so we need 1,840 electrons to equal the mass of 1 proton. That's what that means. In terms of charge, protons have got a charge of +1, and electrons have got a charge of -1, which is why in an atom the number of protons and the number of electrons are the same, because we end up with no charge overall, because the protons and electrons are equal in an atom. And last of all, neutrons are neutral. Neutrons have 0 charge. If we move on now to have a look at how many fundamental particles there are in atoms or ions, depending on what we're looking at, we need to have a recap of how we can use the periodic table to help us do this. So remember, all elements have got their own symbol, and then they've got some numbers. Every element's got 2 different numbers. The numbers are called the atomic number, and that is given the symbol Z, and we've got the mass number, which is given the symbol A. Now the atomic number is the number of protons in an atom, and the mass number is the number of nucleons. That means the number of things in the nucleus, and so it is the number of protons plus the number of neutrons. So it's the sum of those two values. So if we have a look at fluorine down here, in terms of protons, fluorine will have 9. Now we said on the previous page that for atoms, the number of protons and the number of electrons is the same, so that 9 will be for both of these. Zinc will be exactly the same, 9 protons for fluorine, 30 protons for zinc, and 30 electrons as well. Where we'll get some differences over here for sodium, because that 1 plus tells us that sodium is an ion, and more specifically, it is an ion because it has lost 1 electron. And so what that means is it's got 11 protons because that's its atomic number, but it will only have 10 electrons this time because it has lost 1. If we have a look at neutrons, the neutrons is the total number of protons plus the number of neutrons. So if we've got 9 protons in fluorine here, and we've got an atomic mass of 19, a mass number of 19, then the number of neutrons can be found by doing 19 take away 9, which is 10. And we can do 65 take away 30, which is 35 neutrons, and here the number of neutrons is 23 take away 11, which is 12 on there. So the neutrons is the atomic mass number, take away the atomic number over there, the big number, take away the small number on there. We're going to have a look now at some more complicated particles called isotopes. Now, isotopes are particles that have got the same number of protons but different numbers of neutrons. And so I've got some examples here for us to work out. So the protons in these substances, nice and easy, 6 for all of them because the atomic number is 6 every single time. The electrons is also 6 for every single one of these, and the neutrons this time is going to be different. 12 take away 6 is going to give us 6 neutrons for this one, 13 take away 6 is going to give us 7 neutrons on here, and 14 take away 6 is going to give us 8. If we have a look at bromine down here, bromine has got 35 protons in both cases, it's got 35 electrons in both cases, and this one is going to have 44 neutrons, and this one is going to have 46 neutrons on here. Now, a really important thing about isotopes is their reactivity. And actually, reactivity is governed by the one particle which isn't mentioned in the definition of what isotopes are, which is electrons. And the fact that these 3 isotopes of carbon have all got the same number of electrons, they will react in the same way chemically, irrespective of the fact that they're slightly different masses on there. And the same would be true for the bromine. Those 2 bromine atoms would react in the same way because they have both got 35 electrons. We're going to move on now to have a look at electron configuration, which is a fancy way of saying how are the electrons organised around the nucleus of an atom. Now we know at GCSE that these are organised in shells, and you might have also called them energy levels too, and we'll find out a little bit later why we bother calling them energy levels instead of shells. Now for carbon, carbon has got 6 electrons, and it's got 2 electrons in the first shell, and it's got 4 in the second shell. So simple electron configuration, sort of GCSE level, would have had us listing them as 2, 4. Now lithium, which has got 3 electrons, would put 2 electrons in the first energy level or shell and 1 in the second one, and the electron configuration would be this. Lithium plus, which once again is an ion, it's positive still, so that means it's lost an electron. It would have only 2 electrons, and so its electron configuration would be 2, with a plus like that. Now this idea has evolved into a more sophisticated model, mostly because we discovered that electrons in a particular energy level are actually not all the same. Now at GCSE level you're keeping the model simple, so this is what we've considered so far, but what we're going to move on to now is looking at the slightly more complicated model. So first up, if we consider the electron shell model again, we know from GCSE level that this shell can hold 2 electrons and the second shell can hold 8 electrons. Now what you were not taught at GCSE level is actually the third shell can hold 18 electrons and not actually 8, which is what you were taught. But what we were careful to do is only consider the atoms up to number 20, and so this rule, this extra complication, didn't actually come up. It wasn't an issue on there. Now the electron shells that we've just been looking at, the first, the second and the third, they will all have different amounts of energy because of how far they are away from the nucleus. The first electron shell has got less energy than the second, and that has got less energy than the third. And that is why we can call them energy levels instead of shells, because the first shell has got less energy and the second has got a higher energy level and the third is a higher energy level still. This gets even more complicated because electrons in different shells have got different amounts of energy, and so we can take our energy level diagram and actually add an extra level of detail to it. Instead of just looking at energy levels, we can look at sublevels, sometimes also called subshells. Now, the first one's nice and easy. The first sublevel is the same as the first energy level, but it immediately gets complicated after that first level because these levels are divided into the sublevels, which have got different names, and their names are S, P, D and F. They don't all have all 4 of those different names, but they do, starting from the second energy level, start to have some variety. So in the second energy level, we've got the S sublevel and the P sublevel, and they've got different amounts of energy, so the electrons in the second energy level aren't all the same. The electrons in the third energy level aren't all the same either. We've actually got 3 sublevels on here. We've got the S, we've got the P, and we've got the D sublevels on there. And just to go back to the number of electrons that an energy level can hold, there's actually a rule that you can remember where the number of electrons is equal to 2n squared, where n is the number for the energy level. And so what that means is that if we are in the second energy level, we've got 2 lots of n squared. So 2 times 2 is 4, then times by 2 again gives us our 8 that we have in the second energy level. And for the third energy level, we've got 3 squared because it's n squared, which makes 9. We're then doubling it, which makes us our 18 electrons that we can have in each energy level. We're going to look in a bit more detail now at what these sublevels are actually like. And before we can do that, we need to recognise, in fact, that electrons, as we know it at GCSE, we don't quite consider them in the same way. We don't consider them to be a particle anymore, but a cloud of negative charge. And an electron fills a particular volume of space called an atomic orbital. And different atomic orbitals have got different energy levels. And each atomic orbital has got a number that tells us what energy level it corresponds to. So that might be a 1 or a 2 or a 3. But the atomic orbitals have all got different shapes as well, which in turn have got slightly different energy levels. And these are called sublevels that I've mentioned before. And we refer to these as S or P or D or F. And these orbitals have all got different shapes, which I'm going to have a go at drawing now. So first up, the S orbital is actually just a spherical shape, so that's nice and easy to remember, S for spherical. The next ones are p orbitals. Now p orbitals, there's actually 3 different types of p orbital, and they each follow one of the x, y and z planes on here. So that's a px orbital, and then we've got a pz orbital that goes on the z-axis up there, and then last of all we've got a py orbital on there. So those are 3 different p orbitals that we've got. And then the last type of orbital that you need to be aware of is the d orbital. Now they're really complicated to draw, so I'm not going to draw them whilst doing this video, but except to do one, which is my favourite one, which is where we've got one part of the orbital goes up the z-axis, and then another part sort of circles around like a hula hoop over there. But just, we need to know that there are 5 different d orbitals on there. Now let's take a look at these orbitals represented in our energy level diagrams. As I said before, the first energy level consists of a single s orbital, and that's what we're showing on here. And the second one is split into 2s and 2p, and then the third one is split into 3s, 3p, and up here 3d on here. Now we've got some rules that we need to recognise. So first up, each atomic orbital can only hold a maximum of 2 electrons. And the s orbital, since there is only one orbital in the s sublevel and each one can only hold 2 electrons, then the number of electrons in total in an s orbital in the s sublevel is 2. In the p sublevel, because there are 3 different orbitals in the p sublevel, as we can see down here, that means the p sublevel can hold a total of 6 electrons. And then the d sublevel, because there are 5 different orbitals in the d sublevel, that means that the d subshell can hold a total of 10 electrons on there. And then if we quickly note that in the third energy level there is one p subshell, one s subshell and one d subshell, then it's easy to see now why the third energy level can hold a total of 18 electrons in those different 9 orbitals on here. One last other thing to note is actually the slightly weird thing, which is that the 4s has got less energy than the 3d, because each one of these is ranked in terms of increasing energy as we go up here. They have more energy, more energy, more energy, and the 4s has got less energy than the 3d, although that does change when ions are formed. Just a little bit more detail about electrons. Electrons are said to have a property of spin. Now it's really important to note that the electrons aren't actually spinning, but it is to do with their revolutions that they make around the centre of the nucleus. Now, to do with this property of spin, we've got 2 electrons in the same orbital and they have got opposite spins. And what we do to represent that is we use arrows, and we use one arrow up, we call that spin up, and we have another arrow pointing down, and we call that spin down. Now let's have a look at how we put electrons into their places around the nucleus of an atom. So there's 3 rules here. Mostly there's 2 rules, but I've called it 3. So the first rule is that you must always fill the lower energy levels first, and that's because the lower energy levels are more stable, and that's where they will go, the electrons. The second rule is that when you're putting electrons into orbitals, you fill them singly before you pair them up. So that means you put them in one at a time. And then there's rule 3, which is just a reminder rule really, which is that you put 2 electrons into an orbital and then it is full. Now let's have a look at an example on here. If we consider first of all carbon, which has got 6 electrons to put in, we've got the 1s subshell. We put 2 electrons into there and then it is full. And we've got 4 more to put in, so we put 2 into the 2s sublevel and then that is full. And then last of all we've got 2 more electrons and we put them into our 2p subshell on there. We don't need to fill that up. And if we have a look at oxygen, which has got 8 electrons, it's the same thing here with the 1s, the same thing here with the 2s, and then when we get to the 2p, because we've only used 4 electrons down here, we need to put another 4 into the 2s sub-level on here. And so we've put 3 in, and that's our single occupancy, and so we don't have a choice now, we have to put the 4th electron into there, and we get this double occupancy, which does affect a quality of oxygen that we'll come to later. We can write the electron structure or configuration in a similar way, but more complicated to what we were doing at GCSE level. So lithium has got 3 electrons, and so we need to put those into their sublevels. So the first 2 electrons will go into the 1s sublevel, and the second sublevel is now needed to have 1 electron in it, and that is now full. What you've got is you've got the powers in a way, because they're always up in the air numbers, they're not down on the line, that is equal to the total number of electrons that we've got in our particular atom, so 3 for lithium on here. And if we have a look at sodium, which has got 11 electrons in total, that will be 1s2, then that's full, 2s2, then that's full, 2p6, and that so far, if we're keeping track, is 2 and 2 and 6, which makes 10, which means we need one more electron, and 3s1 gives us our 11 electrons in total. For carbon, we have got 6 electrons, so we write 1s2, 2s2, 2p4, and that's then done. We don't need to do all this up here. This was just me keeping track of the total number of electrons for you. You don't write that in the electron configuration. For argon, argon's actually got 18 electrons, so that's a little bit lengthier. And that's the first 10 electrons done on there. And then the next 2, and then the next 6, and that's done on there. That's a total of 18 electrons on here. Iron has got even more electrons, it's got 26, and so the first 18 will be exactly the same as argon, so no extra thought needed on there. And then we've got another 8 electrons to put in, and so we need to get to that rule where you fill the 4s electrons before you fill the 3d. So we've got 4s2, 3d6 on there, and that's our total number of electrons. Now, even though we fill the 4s before the 3d, what we should really do, though, is we should not have the 4s first. We should have the 3d6 first and the 4s2, because as soon as they become occupied, the 4s actually gains a little bit of energy, which causes an issue that we're going to come across in just a moment. Last of all, to do with these electronic structures, we can indicate something about our elements that we have been looking at, and we can refer to them by the identity of their outer electrons. So lithium and sodium are referred to as s-block elements because their outer electron is in an s sublevel, and carbon and argon are referred to as p-block elements for the same reason. Their outer electrons are in a p sublevel. Iron is referred to as a d-block element because its outer electrons are in a d sublevel. It's got an incomplete d sublevel, which is one of the characteristics of the transition elements. And you can navigate your way around that by looking at the periodic table, because the S block is everything in group 1 and group 2, the P block is group 3 to group 8, and then the D block is the transition elements on there, or the transition metals they're sometimes referred to. Now, as I've already said about transition metals, there are 2 rules about the transition metals. You always put the 4s electrons in before you put the 3d in, although you do usually write the 3d first as you're listing them, and then you remove the electrons from the 4s before the 3d. So that's relevant if you're working out the electronic structure of some particular transition metal ions. There are 2 exceptions to the filling rules that you need to be aware of, and those exceptions are for chromium and for copper. So you would expect chromium to have the electron structure 3d4 4s2, and you'd expect copper to be 3d9 4s2, but actually that's not right, because chromium and copper would get more stability if they do something slightly different, and what they have is they have 3d5 4s1 for chromium and 3d10 4s1 for copper, and that precisely full D energy sublevel and that half full D sublevel gives the elements extra stability that they wouldn't have if it was almost full or almost half full. So these are actually more stable, and so this is the organisation that we get for chromium and for copper in terms of their electrons, and those are 2 exceptions that you need to know of. Now let's have a look at ionisation energy. And the ionisation energy, obviously it's the amount of energy because that's in its name, but it's the energy required to remove 1 mole of electrons from a mole of gaseous atoms. Now, what does that actually mean? Well, what that means is the electron that gets removed is no longer a part of that atom anymore. So if we just consider something simple and small, let's do lithium on there. It's got 3 electrons. If we're going to ionize lithium, we have to give lithium more energy to get this electron to jump, not just up a few sub-levels or a few energy levels, but we actually have to get it to jump so far that it has left all the energy levels behind. So we've given it enough energy to make that leap from what's called the ground state, where the element where it has its electrons normally, to those electrons aren't part of that atom anymore. And this energy level infinity, that's kind of considered to be the outside of the atom. So when you're ionizing something, you're giving the electron enough energy to leap from where it normally is in the ground state, past all the other energy levels, past the outer energy level, and it's gone. And so that's the ionization energy of a particular substance. And what you can see from this diagram is if something's outer electrons was in a d sub-level, the amount of energy needed to make that electron leave the atom actually wouldn't be as much energy as if it was down here in the 2s, because that amount of energy, that energy change given the symbol delta E, is obviously different depending on if you're in a higher energy like this one or a lower energy like that one. And so ionization energy varies from atom to atom. And these numbers that we have, they're all measured with the units in kilojoules per mole of that substance, kilojoules per mole. In terms of ionization energy, I was just looking at taking 1 electron away from a particular element, but you don't always have to limit it to 1 electron. You might take away more than 1 electron. Now, the first electron you take away is called the first ionization energy, and the equation that you have to write to represent the first ionization energy always has the element on the left-hand side. The element has to be in the gaseous state, and then it turns into an ion, which is also in the gaseous state, and we lose an electron. So that's the first ionization. The second ionization energy is very logically, you've taken 1 electron away, and so you've got your gaseous ion. We're going to take another electron away from it as well to leave us with a gaseous ion that has lost 2 electrons and so is therefore a 2+ ion, and we get our final electron on there, just the 1 electron on here. And last of all, for my examples, the third ionization energy, we take an ion that's already lost 2 electrons, so it's a 2+ ion, it loses another electron, and so it becomes a 3+ ion this time, losing another electron on here. In terms of comparing these ionization energies to each other, the first ionization energy is always the smallest number. And that's because we're taking an electron away from a neutral atom. Then the second ionization energy is larger than the first, and that's because the electron is being taken away from something that is a positive ion. And so what that means is, because it's a positive ion, we've got greater electrostatic forces of attraction because we've got something that is positive and we're trying to take that negative electron away from it, and there's really strong electrostatic forces on here. And it follows that the third ionization energy is going to be larger still because we're taking an electron away from something that is 2+, so it's got an even stronger positive charge and even greater attraction for electrons. Now, what can ionization energy be used for? So the first thing is it provides us with evidence for the electron shell model for atomic theory. And so if we consider sodium, which has got 11 electrons in all of its energy levels, we can investigate what the ionisation energy is for sodium with each successive electron that we remove. So the first electron that we remove is really easy to remove. Its ionisation energy is very, very low. The second one is harder. As I've said, you're taking an electron away from something that is positively charged now. The successive next 8 are all quite similar to remove. It gets a little bit higher, but not massively each time. And now it's easy to see the pattern on here that we've got one electron that's very easy to remove, and that's in the 3rd energy level. And then we've got 8 electrons along here, which are reasonably easy to remove, but they get harder as you remove more and more of them, and that's because we're taking electrons from only the 2nd energy level. And then the 1st energy level on here, these are the ones that are hardest to remove because they are very, very close to the nucleus. And so they are experiencing a great deal of attraction from the positive nucleus. Whereas as we go down here, this 3rd energy level, these are really, really shielded electrons from the nucleus's pull. We've got a lot of different kind of layers in the way, blocking the positive attraction of the nucleus to get to those outer electrons in the 3rd energy level. Now, even cleverer than this is if we consider just the electrons in the 2nd energy level, and this time take the log to the base 10 of those ionisation energies, and we plot them successively, what we find this time is that we get 6 electrons, which follow a pretty straightforward pattern on there of ionisation energy, or log of ionisation energy, increasing as you take one electron, then another out. But then we get a leap for the final 2. So even those 8 electrons on here aren't equivalent. And what that gave us our evidence for is that these 6 electrons that are pretty close together in their pattern, they're 2p electrons, whereas these ones on here are 2s. And because the 2s are lower energy, what that means is they are therefore harder to remove, because we have to give them more energy to get them to leave the atom. And of course, they're also closer to the nucleus as well. And so that means that they experience a greater electrostatic attraction from the nucleus's pull. We can also use ionisation energies to work out what group of the periodic table a particular element might be in. What we have to do that is we have to look at successive ionisation energies. And so if we have a look here, we've got our first element where the first ionisation energy is 1000, the second ionisation energy is 1500, then 2000, then 8000, then 9000. And the skill that we have to employ here is we're looking for a big leap, a big gap. And so for me, the big gap here is between the 3rd and the 4th electron removal. And so that means that the first 3 electrons are pretty similar to remove as you go along. They get a bit harder, but we're expecting them to get more difficult to remove. And so what this tells us is that this has got 3 outer energy level electrons, which therefore means it is in group 3 of the periodic table. And if we have a look at this next example here for a different element, we can see we've got 500, we've got 4,500. Well, that's a big leap already because that's got 9 times bigger. So it's a leap of 4,000, it's got 9 times bigger. If we have a track on here, just looking here, this is actually a larger increase of 5,000, but 9,500 to 14,000 is actually only increase of about 50%, whereas this, it got 9 times bigger. So that was a much bigger increase on here. So that means that this 1 electron is present in the outer energy level. And so this is therefore in group 1. And the final thing about ionisation energies that you need to know for A-level chemistry is you need to know about patterns across period 3 and down group 2. Now across period 3, if we consider ionisation energies, the pattern is one of 2, 3, 3. That's quite helpful to remember. And so first up, if we just start, there's no numbers on this graph, this is just showing the general trend. It is an increase of 2 in there, or there's 2 in an increasing pattern. Then there is a dip, and we've got 3 in an increasing pattern, and then there's another dip, and we've got our last 3 elements of period 3 in an increasing pattern. So overall, ionisation energy increases across a period. And the reason for those increases, there's 3 reasons, or 2 reasons and then an end result. And so first up is that we get an increased nuclear charge for each element as you grow across the period. And secondly, the atomic radius decreases each time we move along one element in the periodic table. And then thirdly, it's kind of a reason, is that the electrons are in the same energy level. And so that means that the shielding force that I mentioned before is the exact same for each of these elements as we go across the period. And so overall, there is therefore a stronger attraction between the nucleus and the outer energy level electrons. So this is greater attraction between the nucleus and the outer electrons, because it's not just any old electrons that are being removed, it's the outer electrons. There are, however, 2 dips in our pattern. And the first dip is easier to explain. And when you're asked to explain the cause of a dip, I think it's really useful to work out what the electron arrangement is for the different elements that you're comparing. So we're in period 3, so that means the second element in period 3 has got its outer electron in the 3s2 subshell. Whereas for here, because we've got the third element in group 3, it will be 3s2, 3p1, which means that the outer electron is being removed from a p subshell for this element on the right, whereas the outer electron is being removed from the s electron subshell for the element on the left. And we know that p is a higher energy level, or higher energy I should say, than an s, and so therefore it is easier to remove. Over here, this dip in this region is a little bit harder to explain, but if we have a look again at the electrons, it's 3s2, 3p3, and this one is 3s2, 3p4. And so what we're comparing is p3 to p4. Now, if you remember that rule about the electrons occupying singly before doubly, what that means is in the orbitals, this element on here has got 3 single occupancy orbitals. Whereas down here, this 3p4, we've obviously only got room for 3 electrons to occupy singly, and so the fourth one has to pair up. And because of this thing called double occupancy, these electrons are easier to remove. And that's the reason for that second dip as we move across period 3. Group 2 is actually a little bit easier. It just looks a little bit complicated because the first element that we have, and then the second, and then the third, that's a nice regular trend as atomic number increases. And then it stretches out, and it looks a little bit weird that it's stretching out like this, but actually the only reason for that is that we've moved into the D block, and so the number of electrons in a particular energy level increases from 2 to 8 to 18, and so the pattern isn't quite linear on there. But the general rule certainly is, and that is that ionisation energy decreases down a group. And the reason for that decrease is really similar to the justification across period 3. The atomic radius, though, is increasing. And as a result of that increase in atomic radius, there is weaker attraction between the nucleus and the outer electrons. But as well as that, shielding is also increasing. So that means that the electron shells are blocking the nucleus's attraction for the outer electrons. And both of those factors end up with a weaker electrostatic attraction between the nucleus and the outer electron, which is potentially being removed in the ionisation. And that is the end of this introductory video. The atomic structure topic continues by looking at the mass spectrometer and isotopes in greater depth, so check out that second video when you're ready. Thanks very much. I'll see you next time. Bye bye.